everything we've done so far, the object wants to move in a straight line. And what this does is if I can get my pen to work, is the force is constantly pulling it towards the center, which is what makes it move in that circular shape. So that it's being pulled toward the center, constantly moving in this circle shape. So then whenever we talk about the variables in the equations that we're doing, remember so far what we've studied is we've covered these top three here, which are all part of kinematics, the position, the velocity, and the acceleration. And then in the bottom is part of dynamics where we look at the force. The only thing that's really unique about this one is that acceleration equation. So you could kind of think through like position, if we're dealing with a circle, this distance around the circle is going to be the circumference. That's why the distance is going to be the 2 pi r. Then your velocity, if you remember from the previous chapters, is really position over time. And that's why we get that 2 pi r over t. And then, like I said, this equation is the only unique one that you would kind of have to relearn, that in a circle, the circular acceleration is that tangent velocity squared divided by the radius. And then back down into dynamics, it's still going to be F equals ma, but now this is going to be all of the forces pulling it towards the center of the circle. So what we want to look at then is what, if we're doing F equals ma, what force is actually pulling it towards the center. That's going to change all depending on which type of problem we're doing. Like if you are driving down the road and the road is icy, but you go to make a turn, then that force is not there to pull you towards the center. And that's why you would slide off the road into a ditch. So you can think through that the force pulling you towards the center of the circle is really that force of friction between the tires and the road. If you're looking at the spinning stopper or spinning object, it's whatever the force is. Maybe this is the tension in the string for her as she's pulling on that to make it spin towards the center. If we're talking about orbits, like this is the Earth rotating around the sun, then the Earth is going to have a pull of gravity between the sun and itself. And that's the force that will go into that F equals ma. And we'll talk about that here in a second once we look at one of those problems. So in each of the problems, then it'll be the exact same as the previous ones, where we'll either start with, oops, I just lost my pen there. We'll start with kinematics. It's really hard to write with a mouse. And then find the acceleration using the kinematics, and then use that acceleration to find the forces, which is dynamics, or we'll do the other way again also, where we'll start with forces, work our way to get the acceleration, and go back to the kinematics, okay? So sample problem, you're on the swings at the Lake County Fairgrounds, and it has a circular radius of 5 meters, and you travel around that in 4 seconds. Now, this is not like, if you think through like the kind of swing where you would sit on the swing here and you would swing like this. This is the kind of swing that would be like, let's see if I can draw this here, like this, and they hang down, and then whenever it starts spinning, you spin around like this around it. It's that kind of swing. Does that make sense?
Yes.
So we know a radius here that is that 5 meters, and we know a time, which means we're probably going to start with the kinematics side of that. So if we're looking for acceleration, remember our acceleration is going to be v squared over r. We do know what the radius is, that's going to be the 5, but we don't know the velocity to solve for a. So the next thing we would look at then is, well, our velocity equation is 2 pi r over t. And in that case, we do know everything we need to know. We have the 2 times the pi times the 5 meters divided by the 4 seconds. And then we would punch all of that into our calculator to get those values. So 10 times 3.14 divided by 4 is going to be 785 meters per second. Then we can take and put that back in up here, 785 squared divided by 5. And that gives us an acceleration of 12.32 meters per second squared. So that would be our answer to part A. Then our answer to part B, like I said, now that we have A, we can go into F equals ma and plug in the values to get what that force is acting on the person, that force that's pulling them towards the center of the circle, keeping them going in that circle. So this says use your mass. Remember that to find your mass from chemistry, you would take your number of pounds and divide it by 2.2, because 2.2 pounds per kilograms, or you can just make up a number. The average human is anywhere, like the adult would be anywhere from like 45 kilograms to maybe 100 kilograms. I think the last one that I looked up, the average world adult male is a 70 kilograms. The average United States male is 82 kilograms. Just a small thing on obesity there. So just pick a number and stick it in there. And then you would put your acceleration in the 785, the 1232. Oh, my goodness, I can't write today, huh? 1232. So let's just, for the heck of it, say it's a 70 kilogram person. So 1232 times 70, and that's going to give us a force of 862.4 newtons. Okay, now that's the one where you would start with the kinematics and go to acceleration, and then from there go to dynamics. The next problem is the problem where you would go the other way. So you would start with the dynamics, start with the dynamics and go backwards towards the kinematics. So a car rounds a circular turn of radius 5 meters. So that's my radius. If the road is flat and the coefficient of friction is 0.5, then how fast can the car go without skidding? So if we're starting with that, we're going to go with F equals ma. Remember that this is the force pulling them towards the center. So if here's my turn and my car is coming around this way, then what keeps them from sliding off the road? It's that force of friction. So we would have our force of friction here. The force of friction then becomes what goes into F equals ma. Now, do you remember what the equation for the force of friction was? It was what we did in the lab last week, where we found that that friction is equal to mu force normal, or the coefficient of friction, which is the mu value, times the normal force. So I can substitute that in here also, mu force normal equals ma. And then lastly, I would look and say, hey, if this is a flat surface and my car is just sitting here, or it's moving forward, then how would I find what the normal force is acting on the car? Isn't that going to be equal to the force of gravity, because the car isn't floating or sinking? And so I can take then the next step and say this normal force, I'm going to substitute in the gravity instead. And then lastly, remember that to find that gravity or that weight, we would do the special force of F equals ma, where if this is the force of gravity, this is the acceleration of gravity. So we can convert this into mg. Now, looking at the right side, we're not looking for acceleration, we're looking for how fast, which is a velocity. So remember that the equation that relates the acceleration and the velocity is going to be that a is equal to v squared over r. So I can take and substitute that in, v squared over r here. Interestingly enough, whenever we look at that equation that's at the bottom here, then this guy, both sides have a mass in it. And so it doesn't matter if it's a tricycle or a semi or a really small smart car or anything, that velocity is going to be the same for any of those to be able to stay on the road, because the masses will cancel out of both sides. And then after that, we can just substitute values in. So we can put in our 0.5 as our mu value, 9.8 is our gravity value. We're looking for v, and we know the radius to be 5 meters from that. So then 5 times 0.5 times 9.8 and square rooted, and we end up with a velocity of 4.95 meters per second. And so that would be your answer to that one. So major idea, there's a whole lot of math magic that happened on this side where we're just substituting values in to find that force of friction. But remember, it's not always going to be the friction. Sometimes, like we had over in this slide, it'll be the tension in the string that's pulling it towards the center, or sometimes it'll be the force of gravity pulling it towards the center, whatever you're looking at. Another application to this is, if you guys are drivers, have you ever seen the wavy road signs that have like the mile per hour on the bottom that says this is your new speed limit on the wavy road? This is how they calculate what that is. you can think through that value, that 35 miles per hour, it's not going to be though on a day like today where it's just a bright sunny day and the road is all nice. It's probably going to be like if it is a snowy, icy day or a rainy day where that coefficient is low. And so this would be the top speed on a really ugly day, which is why you could theoretically drive like 50 miles an hour around those curves now and be like, well, I wonder why they put it as 35, because it's really, I can go faster than that. But that's why. It's because it's looking at a lower coefficient of friction value. So major ideas again, remember that you're going either from the kinematics to the dynamics, or you're going from dynamics to kinematics, and it's just going back and forth between all those four equations that are there. And again, only the acceleration is really the new equation from that.